This series of lectures is going to focus on explaining the strength of different acids in terms of their molecular structure and bonding. So there are three questions that we want to think about as we're discussing this topic. The first is, why is HF a weak acid but other hydrogen halides are strong acids? Why is nitric acid a strong acid but nitrous acid, which is related, is a weak acid? And why can carboxylic acids behave as Bronsted acids? So in this discussion, we first want to think about the generic reaction that occurs when something behaves as a Bronsted acid. So acid dissociation must occur, in which the acid, in this case the general acid HA, is broken into a proton and A-, the conjugate base of HA. And we can actually break this reaction down into three steps. And so to understand why behaving as an acid will be favorable, we need to think about the enthalpy change that occurs on going from the acid to the dissociated form of H+ and A-. So the first step is to break the HA bond into a hydrogen atom and an atom of A. And this reaction has an associated enthalpy change, which is the bond dissociation enthalpy for HA. Next, we need to ionize the hydrogen atom to form a proton and an electron, and this enthalpy change corresponds to the ionization enthalpy of hydrogen. And then last, we need to add an electron to A to form the ion A-, and this is related to the electron attachment enthalpy of A. So if we were to add these three enthalpy changes, that would give us the overall enthalpy change for the acid dissociation, and the magnitude of this value, how negative it is going to tell us something about how favorable it is for it to occur. Now, when we look at these three steps, step 2, where we're ionizing a hydrogen atom to form a proton and electron, occurs for every acid, and it's going to have the same value for every acid, and so essentially we can ignore this second step when we're taking into account the enthalpy changes related to acid dissociation. So acid strength is going to end up depending on two things: the strength of the HA bond, so the bond dissociation enthalpy, and the electron attachment enthalpy of A, so that's related to the electron affinity of A. So in the simplest cases, these two effects would work together. So if we have a weak HA bond, that means it's very easy to break the HA bond, and if we have a large electron attachment enthalpy, that means that it's easy to add an electron to the atom A, and so both of those would lead to a strong acid. It's easy to break the HA bond, and it's easy to add an electron to A to form A-. The opposite would be the case where we have a very strong HA bond and a small electron attachment enthalpy. In this case, it's hard to break the HA bond, and it's also hard to add an electron to A, and so this would result in a weak acid. Now, generally speaking, most cases are not this simple. Often the two effects work against each other, so we need to delve a little bit deeper into the enthalpy values to explain the trends that we observe. So the simplest class of acids that we're going to discuss are binary acids. Now, a binary acid is an acid that just contains hydrogen and one other element. And hydrogen halides are an example of these acids. So we mentioned before that HF is a weak acid, whereas the other hydrogen halides are strong acids. And the trend actually is such that moving down the group of the halogens, the hydrogen halide strength increases. So HF is the weakest of them, HI is the strongest. So in order to explain this trend, we want to look at the HX bond strength and the electron attachment enthalpy. Now we can see that the HF bond strength ends up decreasing moving down the group. So HF has the strongest bond, HI has the weakest bond. And we can explain this in terms of the orbitals that actually have to overlap in order to form these bonds. So in HF we have an H1s orbital overlapping with a fluorine 2p orbital. These orbitals are fairly close in energy, and they're fairly close in size as well. So there's a fairly good overlap, resulting in a strong bond. Now moving down the group to HI, we still have a hydrogen 1s orbital overlapping, but in this case it's overlapping with a 5p orbital on the iodine. And in this case, the energy difference is quite large, as is the size difference, and so there's poorer overlap between the hydrogen orbital and the iodine orbital. what results is a weaker HX bond, so the HI bond is significantly weaker than the HF bond. So in terms of solely in terms of bond strengths, we would expect HF to be the weakest acid, it has the hardest bond to break, and HI to be the strongest acid. So the trend in bond strength correlates with the trend in acid strengths. So now let's think about the electron attachment enthalpy. This value becomes less negative moving down the group. So it's most negative for HF and least negative for HI. A more negative electron attachment enthalpy is more favorable, and so would lead to a stronger acid. So HF, which has the most negative electron attachment enthalpy, would be expected to be the strongest acid if we only considered this factor. So the two trends are kind of opposing each other, and so it turns out that the HX bond strength kind of dominates in this, and we can tell this by looking at the sum of the two effects. So if we add the HX bond strength and the electron attachment enthalpy, we get a series of values where HI has the smallest magnitude, the closest to being negative, whereas HF has the largest. And so this tells us that it's most favorable for HI to dissociate into a proton and iodide, and for HF it's least favorable. And so in any case where the two effects are kind of opposing each other, we need to consider the sum of the two enthalpy changes. And in general, for acids in the same group of the periodic table, acid strength is going to increase down the group. And this is because moving down the group, the differences in HA bond strengths are much more significant than the differences in electron attachment enthalpy. And so the differences in HA bond strength are going to be what actually determines the acid strength. So now let's look at the acidity of some second and third period hydrides. So we're looking at the second period hydrides, which are methane, ammonia, water, and HF. And then the third period hydrides, which are silane, phosphine, dihydrogen sulfide, and HCl. Now we see that the bond dissociation energies generally increase going from left to right across the period, and they decrease moving down the group. So the OH bond is stronger than the SH bond. The HF bond is stronger than the HCl bond. So in this case, the bond dissociation energy increases across the period. So considering only bond dissociation energy, we would expect that HF is the weakest acid and methane is the strongest acid. But we also see that the electron attachment enthalpy increases across the period, and so this would correlate with a higher acid strength moving across the period. So again, we have two opposing forces, but it turns out that what prevails in this case is the electron attachment enthalpy. So acid strength increases across the period. Methane is the weakest acid in the second period, and HF is the strongest. And then silane is the weakest in period 3, and HCl is the strongest. Now again, the reasoning for this is that the change in the bond dissociation energy is much larger than the change in electron attachment enthalpy, and so it's the factor that predominates the acid strength. So generally speaking, for binary acids that are in the same period, acid strength is going to increase across the period.